Hi, I'm Gary, and I want to show you how I use Cloudy. Okay, today we're going to extend our existing M16 model into the molecular cloud. To do that, we're going to make some changes. We're going to make the model better and see a few options for controlling output. We have a scheme to control with one command the names of all the save files, and we'll use that set save prefix. Our H plus layer stopped at our default 4,000 degree stopping criteria. We don't want that. We want to go into the molecular cloud. So we have a stop temperature off. So this turns off the stopping criteria based on temperature. We then need some reason to stop. We could set the column density. We could set the thickness of the cloud. What we will do is stop at an AV of 20 magnitudes. This seems to be a very typical stopping criteria for many PDR calculations. So far, we've been using abundances ISM, which is an older set of assumptions about the gas phase abundances in the ISM. We can do far better today. So we'll use a combination of the recent Jenkins metals depletion paper, which has been encoded into Cloudy, and we'll use those depletion factors which depend on environment, together with the best solar abundances to create good gas phase abundances. Then we're going to adjust the grains. We've been using abundances ISM, which is diffuse ISM grains. Grains, as near as we can tell, that are in H2 regions, molecular cloud star forming regions, they have a larger size distribution than the diffuse ISM. So the best case study is Orion, which has an R of about 5.5. So that means either the grains have a deficiency of small particles or a surplus of large particles. So that's built in from studies of Orion. So we use the Orion grains since we're going into a molecular cloud. We haven't turned on pause so far, and we'll use them because pause can be a diagnostic, especially of the interface between the H plus and H naught layers. Then lastly, we have a very large, complete state-of-the-art model of the H2 molecule. It's not on by default. By default, we use some simple approximations from papers that try to fit 3 or 4 or 5 level atoms to the H2 molecule. We can do far better than that, and we'll use the complete H2 molecule. So we'll have the full H2 row vibration spectrum when it come out. Okay, with that, let's modify our input deck and run a model. Okay, here's our homework directory. Let's remind ourselves what we have. We've run m16.in, so we have these save files. I'm going to just copy m16.in over to a new file. I'll just call it m16 PDR since we're going into the PDR. So there it is. Let's have a look what we have in this new file. It's the same as the old file. So we're going to make a series of changes. We want to manage the save files better. So my workflow, I use set save prefix, and I use the name of the model, which would be M16 PDR. So we're going to use this as a prefix for all the save files. So let's go find the save files. Here they are. So we're going to delete this prefix, keep going. So now our save files are going to use the prefix entered between double quotes here, and it's the only place it appears. So all the save files have no file name, and that prefix will be used. So this makes it easier to do special cases. You want to do a one-off model, you can just change the prefix. We're going to turn off the temperature limit and set a new stopping limit. Both affect the geometry of what we compute. So we want to do here, stop temperature off. So that tells the code that keep going no matter how cold it gets. It'll go down to the CMB temperature. We've turned that off, so you need to find another stopping criteria. So let's stop at an AV of 20 magnitudes. Next, we want to change our abundances. So I'm going to comment out these abundances. If we don't set that, we'll use solar abundances, and there'll be another video about the abundance mixtures that are used. And so we, by default, use a fairly recent set of results on solar abundances. We want to do interstellar depletions. So we're going to use the famous Jenkins 2009 paper where he fits an F star to variable depletions in the ISM. So we're going to do metals. Metals are everything heavier than hydrogen and helium. Deplete. We're going to deplete the metals with the Jenkins 2009 paper, and we need to set an F star. This is his parameter that he specifies. So it has 0.5. So that's his free parameter for the range of depletions that he sees. Next, we need to turn on grains. Our abundances ISM turned on grains appropriate for the diffuse ISM. This is a molecular cloud in a star-forming region, so we probably better use abundances that are grains that are more appropriate for there. So we'll use a built-in command, grains Orion. And so that uses grain opacities that satisfy the observations of the line of sight to the central stars in the Orion Nebula. These grains have a very large value of R, 5.5. So that means they have either a deficiency of small grains or a surplus of large grains. So we'll use Orion grains since this is the star forming region. And then last, we'll turn on grains PAW, and we'll increase the PAW abundance by a factor of 3, which is this is a different than we assume by default if you specify nothing, but it is in better agreement with more recent observations of PAWs. So instead of using abundances ISM, which did a lot of things, some of which you might not agree with, we're going to explicitly put these things step by step out here. Okay, with that, lastly, we want to enable our large molecule, our large H2 molecule. And the command for that is database H2. That command has a history to it and might seem a bit weird, but that's what it is. And so by default, we use very simple 3, 4, 5 level approximations to the H2 molecule. That's really not very accurate. This will do all the bound row vibration levels in the ground electronic state, and it does many of the Lyman-Werner bands, and would be a much more satisfactory representation of H2. And we get the full vibration, rotation, electronic spectrum of H2. Okay, with that, let's set aside our model and run it. It will take a while. We're going a long distance into the molecular cloud, and let's let it bake. See you in the next video.